then there's going to be a recommendation use case that he'll talk about. So, Larry, can you give us some background about yourself and your company first, and then we'd be eager to hear more about the product.
Yes. Well, in fact, I'll tell you a little bit about the company in one of the slides.
Okay.
I am a professor at the Technical University of Catalunya, which is based in Barcelona, Catalunya, by the way. And I have been the CEO of Sparxy since its beginning. It started in 2010. So I've been doing both research and the management of the company together with a team of great people. So we've been developing a very interesting, I think, graph database and a number of projects around it that have allowed us to have, I think, a very solid and interesting product, because it's the only graph database for pure edge computing. And what I mean by pure edge computing, I mean embedded and mobile devices that runs at a fairly good speed and provides quite a lot of functionalities, right? Both for any operating system and version of the operating systems in edge. The very same graph database runs on servers, so it's very lightweight, and I'll tell you a little bit about the database. So
Okay.
if you don't mind, I can start with the presentation here. If you can go ahead one slide. Okay, so I'm going to talk a little bit about the Sparxy. The graph database that we have is called Sparxy, as when you see a spark lighting your future, let's say. I'll talk a little bit about our customers, and I'm going to get in depth into the use cases that we have. I can talk a little bit about the patent, but if you don't want, I can skip that, as well as the benchmarking part that we've been working on. And finally, I'll make some discussion on edge and cloud, what should be on one side or the other. Yeah, okay, so let's go on. One more. So Sparxy is a spin-out of the Technical University of Catalunya. Its main product is Sparxy, the graph database that we have, and I'm going to talk about. We also work on smart mobility, and the reason for that is quite obvious. A map can be represented as a graph, so we've been working on that, as well as in optimization issues for logistics. As I was telling you a little a while ago, Sparxy is the only graph database for edge devices, both embedded in and mobile. And we have a few customers. Bosch is the most, the best known for you. The other ones are, I would say, local or European based. And we have been involved in many European community funded projects, which give you a lot of investment for not for nothing, but for work, but it's very much oriented to your objectives, right? So next slide. Well, I would say a couple of them. So what are the most relevant Sparxy features? It has a very small footprint, both for software and data. And that's relevant because when you come to having a graph database in a mobile device, this is very important. the interesting thing about the graph database is that it's based on bitmap structures, which can be compressed very easily, and they give you very high performance because most of the work that has to be done is reduced to basic arithmetic. And when you are getting into mobile devices where you have very simplistic or more simplistic processors, having arithmetic and logic operations simplifies your life. And this is the case for the type of data structures that we manage. It is compiled for different operating systems, iOS, Android, Linux, Windows, and with different interfaces, as you can see here. We recently released a version of Sparxy Cipher that we are going to evolve in the next years. So some of the characteristics that are interesting, and they are related in some cases with one of the use cases I'm going to explain later, are, for instance, the recovery and encryption, and some of the algorithms that we are providing with a graph database. Because if you are looking at the mobile or the edge computing oriented to the car industry, they need fast recovery and certain recovery whenever the car stops in the middle of a transaction with the database. And also it requires encryption, because if the car is sold to a third party, or if it is stolen, you don't want a third party to know about the characteristics of the driver who was previous to use the car to the thief or second-hand user. Given that we are in the car-oriented industry, we are in the process of accomplishing a few automotive standards, which are, I don't know if you are familiar with, but it's a SPICE. Basically, a SPICE has the objective to provide traceability, so that whatever failure in the system can be traced back to its coding origin. And that's important, because in the car industry, you need to be certain on where to find your bugs. Okay, next slide. Okay, so these are the customers we had and have. For us, the more relevant, we've been collaborating with Oracle in the graph database aspects, with IBM in the relational aspects, but we have also worked with different banks and collaborated, of course, with different universities. And Bosch, I think it is now our largest customer. Okay, so let's go into the use cases. The first one I'm going to talk about is the Bosch use case. And the main question here is, can an infotainment system help to avoid car accidents? So in the next, if you click again. So the idea with the infotainment system is that we keep a knowledge base about the voice and behavior of the driver within the infotainment system, the processor, the processing capability, the embedded system, right? We basically provide the technology, and this means that we are not getting into the actual recommender or the actual software that does the coding for the specific issues they want to solve. But as you can understand, well, we've been working with Bosch now for close to 4 years, and we have a product at this moment, a product that they are selling to different OEMs. And these guys, the main work that we've been doing with them has been basically in providing a very good technology, a technology that does really what they needed in a fast way, in a reliable way, in a way that allows them to be sure about the fact that this is going to respond in the way it has to respond. And one curious thing is that the first year that we were working with them, we didn't know they were Bosch. They were just testing us. And after a year, they told us who they were, and we continued working in the same way. But they got into deeper aspects of the database, and we were able to provide them with a much better version of our software. So growing with them has been a pleasure, because these guys are really not only interesting in terms of the type of problems they put on top of the table, but also in terms of the way they deal with any relationship with a provider. And this was the case. So the interesting thing about this use case, and you will see different use cases with different characteristics, is the fact that we have to deal with a very little amount of memory. And that's important. Our graph database is out of core and it's persistent. So being that it is out of core, we made sure that it could fit in a few pages of the operating system. The data could fit in a very few pages, the data that we are using. And it exploits very much locality in a way that allows us to have a very good performance for small devices. Next, if you click again, as I told you, the recovery features make the database resilient to abrupt vehicle stops. And if you click again, the encryption issue makes sure that data are preserved from leakage or data theft, which is important, well, everywhere, of course, for a vendor to provide these characteristics to the user, but especially in Europe, where you know that the restrictions about data privacy are significant, and all the countries in Europe have to follow the same regulation, which is GDPR, which is General Data Protection Regulation, and this is an important case for us. So this is a basic idea. I cannot tell you much about how the algorithms within the software they engaged are implemented, but I can tell you that they use the graph database in order to predict what the user is going to do next and what the user is going to say, provided that they have they use a sentence and they learn about how the person is conveying the talk that the person is. They are working on other aspects, but at this moment, this is what they can offer. Okay, let's go to the next use case. The next use case is about Discover. Discover is an independent, a third-party company. These guys rely on the fact that 85% of the users do not plan their trip at a micro level, but they only plan where they go. So they say, okay, I'm going to Barcelona, but they never think, what can I do in Barcelona, right? So what this application is doing is providing a timeline that you can see the screenshots of the application. The leftmost one is the timeline that we provide. It's similar to Twitter in such a way that people can see whatever is close to them wherever they are, right? And that's interesting because this allows people to plan at a very microscopic level whenever they are in a place and say, okay, what can I do now that I am in this square? So the idea here is that recommendation plays a very important role, because if people are staying at a hotel, for instance, they don't want to see the same points of interest every time they open the application, but they also want to know about interesting places for their own characteristics, for what they like. People who like museums are not probably going to like walking, or maybe they do, but people who like graffiti, for instance, it's difficult that they like to go to some type of museum. So we have to know about that, and we have to learn about their characteristics. So this is where Sparxy plays an important role. Next click. Okay, so what we do is basically providing a knowledge base of the individual in the mobile device. So the mobile device keeps recording, and this is the graph that you see here is an example of a very simplistic example of what a guy is doing. So the guy visited point of interest 1, and I'll tell you what type of what visit means. So someone visits point of interest 1, and point of interest 1 is associated to tags 1, 2, and 9. And then after some time, the guy visits again point 2, and this one is associated to other tags, in such a way that this graph keeps growing. Whenever we want to understand what we can show the person, what we do is computing a personalized weighted page rank on the graph that we have in the mobile device. We don't do that in the server, we do that in the mobile device, and provide the ranking of tags together with the points of interest that the person has already visited or valued or whatever, right? Why do we do this in this way? So the idea is that the ranking of tags, is going to tell the server what points of interest have to be sent to the mobile device. So that's going to give an order and maybe also a reduction in the number of points of interest. And the points of interest that have already been visited are going to restrict the points of interest that are going to be provided in such a way that we may randomly provide points of interest that have already been visited, but not necessarily. So from the mobile device, every time that we make that the guy opens the application, we send a request to the server with these tags ranked, thanks to the computation that has been done in the mobile device with this page rank, this weighted page rank. And the server sends back a global / personal recommendation algorithm by which both these personal tastes and the global amount of visits of these points of interest, how the algorithm puts them together, and this is sent to the mobile device again. So what are these type of interactions? So there are interactions like likes, there are comments, a person can save a point of interest so that in this save list, whenever the person visits the place, these are going to pop up. And finally, a person can click on top of a point of interest and get further information. So what we do is giving different weights to the different types of interactions. So a like is going to be less than a comment, and save is going to be less than a comment, because a save means that this person is really interested in that very place, right? So as you can see, in the previous use case, we had the graph database only in the embedded system. In this case, we have the graph database in the mobile device, but at the same time, it communicates with the server, and some of the computations are done in the mobile device. This is relevant because although the amount of information that we may be sending might not be reduced depending on the strategy that we follow, at least part of the computations are done in the mobile device. And at the same time, we can keep this knowledge base in the mobile device and save it if we want in the cloud server. Okay. By the way, if you have any question, just go ahead. Okay.
Yeah, Larry, I just have a quick
Yes,
question.
go ahead. Sure.
I know that you're not directly addressing this problem, but what I've heard about the current generation of cars is that the code is just a huge sprawl, and it's a very complex environment considering what it should be. And it sounds like your product is quite efficient by comparison. So you've got the personalization that you're doing relative to the external environment. What about the in-car environment? Is Bosch doing something on that front, or have you thought about that at all?
Yeah, well, in fact, this is something that I've proposed them. Bosch is under the restructuring of their work groups. And instead of having different divisions in different areas of the car, they are going to have a single division for cars. In such a way that the people who we are collaborating with in the infotainment system, they are talking with their mates in this complete car division to see if they can use our graph database for the whole car as a knowledge base for the car. Yeah.
Excellent.
Mm-hmm.
Other
Okay,
questions at
so
this
the
point?
next. Oh, yes, please.
Raise your hands if you want to.
Well, I'll go without raising my hand. So is this an RDF triple store graph? No, okay.
It's pure graph. It's pure graph. Yes. So it's a multi-graph. In fact, nodes can be of different types. Edges can be of different types. You can have multiple, sorry, multiple edges between two nodes. And all nodes and edges can be attributed. So they can hold different attributes, right? So
Okay.
yeah, that's it.
And the other thing, when
Any
you
other
started
question?
down, the idea that the entertainment system could reduce accidents. I mean, it seems like its main job is to encourage them, but it seems like
Yes.
merely sensing the fact that you're in heavy traffic, it should shut it off or something. But I guess that's not where they're going.
Well, in fact, the idea is that the infotainment system by nature is something that you need to interact with. So with the use of the graph and the use of the knowledge base, what they try to do is to reduce the amount of interactions, right?
Yeah.
So this, in a sense, I cannot tell you how much, but in a sense, is probably the most relevant objective for them, right?
Mm-hmm. Yep.
Peter's got his hand up.
Yeah, Peter.
Hi, I was just wanting clarity, Joseph, on what you just said about it being like a multi-graph, because you didn't really home in on Dave's question about whether it deals with RDF, which is triples, but what you seem to also be saying is that edges can be annotated, which begins to look like either a labeled property graph or something that would be a RDF star. And I was wondering if well, could you tell me a little bit more about it, please?
So yeah, well, within the graph, you can have edges with any type, well, not any type, but certainly different types of attributes. One interesting thing is that we are allowing now in the new versions embeddings in the nodes in such a way that you can structure. And although we could support, we don't now directly support RDF, but we could support RDF with a proper interface. That would be easy. But our objective is not to substitute RDF; it's to create a pure graph engine that allows us to have the characteristics of a graph engine with algorithmics that give you solutions not only for the mobile or embedded system, but as well for a server. But our focus now is very much oriented to the embedded system, right?
So is it a bit like Datomic, for example?
I don't know this technology. I'm sorry about that.
That's okay.
But I am interested in that.
Yeah, Datomic is a mutable data store. And so I'm wondering, does your database have any immutability capability or log file storage capability? No.
No. Okay.
Okay, I think
Okay, I can go
that's
ahead.
all the questions
Sorry.
for now. Yeah.
Thank you, Peter. Thank you. Okay, so the idea with micro routing is that whenever you do optimization, the routing system takes you to the point that you are trying to get to. But if you drive a car, most of the times you are looking for a parking space, especially in Europe, where space is much more compressed than in the Americas, and it's much more difficult to find a parking spot. So the idea here is that given that most infotainment systems contain maps, having and most of the times is open data, having the information about where the parking spots can be found, we can do micro routing around the point that we are heading to, in such a way that we allow the driver to find a spot. This can be done in the mobile device, right? So if the global routing is done in a server because you are part of a fleet and this fleet has to have a number of different routes optimized globally, then we can provide this specific routing in the mobile device or the embedded system of the infotainment system. Okay, that's one. Let's go ahead. Next. Well, this was an example. Given that you have access to these slides, you can share them with the rest of the people. Another example is the use of a knowledge base in a web application session, in such a way that we create a knowledge base of what's happening in that session, in such a way that we provide recommendations. In this case, it is a film, but it can be other types of recommendations, like when you are visiting an Amazon page where you have different products, and this can be done through a edge knowledge base that keeps evolving only for that session. So it keeps the privacy of the person, and it really can optimize the idea of providing recommendations oriented to the specific moment. Because as you know, whenever you search for a journey, for a trip, for a flight, for instance, they keep sending you advertisements about this flight or other flights, and you don't want that. So maybe having this type of very oriented edge type of recommendation based on a knowledge base in the edge in the web app can be an interesting asset, right? We are doing that. We are now having a pilot of that with a company. Okay, next. If I'm not wrong, yeah, well, that's what I was explaining you. Okay, so all this is based on a patent that our university placed. The idea is, I can go into the details of this, or if you want to discuss about the use cases, and you prefer to go into the use cases, given that this is going to be given to you, you can go into that. And if you want to discuss the patent afterwards with me, I'm open to discuss that. But the basic idea here is that we are using just bitmaps to represent everything. So the graph, the links between the nodes, everything is a bitmap, and it's based all in a single structure. If you go ahead, you will see that one more. So whatever value here in red is telling, so if you have, for instance, the word Barcelona as an attribute of a node, this object ID tells you which are the nodes that contain this word, this specific word. So you have Barcelona, you have, I don't know, Phoenix, and you have New York. So each ID is going to tell you where this value is contained. So this it has different characteristics. On one side, these bitmaps can be compressed very much because the word Barcelona doesn't appear everywhere. It appears in very few nodes. And also, it allows you to have each item only represented once, which really simplifies everything. So there is compaction on both sides. Of course, we have an index here for the value, but also the object ID. Whenever you want to know what is the content of object ID number 1, you know that it's A, it's Barcelona, for instance, right? So everything within the graph database is based on this structure that we call link, okay? And you can go ahead one slide. Next. Okay, so I'm not going to get into the details here, but you can see that there are different types of nodes. You have articles and you have images, and you have different types of edges, references, and contains the edge telling you that this article contains an image. Okay, so they all have different data within. You see that, for instance, in this article, where the language is French, you have the same word for Europe than in this one, which is in English. So we are going to have in the title attribute, we are only going to have one word, which is Europe, but the language attribute is going to let us distinguish between the two nodes. Okay, so that in a sense is what I was telling you, the simplification of the whole of the content within the database, right? So let's go ahead one more. So here I'm not going to get into the details, but what sorry about that. What we have here is all the links, all the structures that I was telling you for different types of information that we are going to store in the database. One is the object, so we have nodes. We have nodes of type article and nodes of type image. We have edges of type reference and contains, and you see that all of them are always represented with the same data structure. And that's important because the access methods that we are going to use are very effective and are very, they are implemented in a way that they are very fast. I'm going to, then all the attributes are also represented in the same type of structure, and the relationships also are telling you what are the links between nodes and between nodes in such a way that these relationships tell us which is the tail of the edge and which is the head of the edge, if they are directed, okay? Okay, so let's go into benchmark. Oh, one interesting thing is that you don't need to go back, but the bitmaps and the way we represent them, they are clustered into chunks of 32 bits in such a way that these chunks of 32 bits can be put into pages, and this is what gives us the actual locality, the ability to exploit locality from them, because the bitmaps can be compressed, but at the same time they can be chunked, they can be chopped into smaller pieces that can be really used with high locality. So going into the benchmarking thing, we have been, I don't know if you've heard of the LDBC Linked Data Benchmark Council organization. I recommend you to take a look at it. There's a lot of free data. Well, there is one interesting data generator, which is DataGen. It's a benchmarking effort for graph and RDF technologies. As an effort, it has this was paid by the European Commission, and at this moment we have companies like IBM, Oracle, big players in the market for graph management technologies. And we have 3 different types of benchmarks. And the more relevant one is the social network benchmark, okay, which allows you to understand for very smaller transactions how the database or how the storage device that you are using is performing together with the software. Okay, I'm not going to get into the detail of this, but I recommend you to get into LDBC, which is a very interesting organization, and it's very, very lively, right? Okay, next slide. And this is the end of my discussion. So whenever we are talking about edge and cloud, we have to measure very well what we are putting on the edge and we are putting on the server. Whatever data that we put on the edge, we have to make sure that it allows us to compute whatever characteristic of the data that we have in the edge, and also saves us some money. So it saves us computational time, computational cycles from the cloud. As you saw in the Discover example, the fact that we are computing the page rank in the mobile device is saving us a number of computational cycles in the server, in the cloud, which at the end is going to be beneficial for the company that is providing the service. Of course, computing the page rank must not be very heavy, and this is the case. In our case, we are saving the computation of a page rank for 1,000 nodes and a number of edges similar to that is less than a second. So in a mobile device, right? So that's very convenient for the recommendation process. Okay, so I'm not going to get into the detail, but things that have to be taken into account whenever we decide where to put data are whether we put the data in a centralized way or we distribute it along the different personal devices. We all know about that, but I'm not going to get into the detail of this because I'm sure that there must be a lot of discussion if you want to discuss with me about the characteristics of not only the graph database but also the use cases that I explained. But I think that these are aspects that have to be taken into account. You can go one more ahead and. Okay. Well, if you have any question or you want to have a discussion on what I explained, I could go into more details, but I thought that giving this overview was enough for starting a discussion.
Yeah, I really appreciate it, Larry. And you've opened up some areas that are really we haven't thought a lot about before.
Okay.
The question I'd have for you is on the edge versus the centralized storage. And I'm wondering, you know, self-sovereign identity has been kicked around quite a bit. The Internet Identity Workshop has done a lot of work on that, as well as the DIF, the Decentralized Identity Foundation. Is there a connection between what you're doing and those organizations?
Not at all, but by the names that you are pronouncing, I understand that this is really relevant for these organizations, right? So, yeah, I think that an interesting aspect of what we are proposing is the fact that you can make recommendations totally private if you want, and that's significant, right? Because at the end. Not everyone, but many people are conscious of their privacy and they want to keep this private, right? You may still keep recommending. So we are now, I didn't put this example, but we are now working with a bank and they want to recommend products just from the mobile device. So the mobile device is going to keep a knowledge base. They are going to provide all the products they have within the mobile device, and the recommendation is going to be on within the mobile device without having any connection back to their servers. So that makes conscious recommendations, right? In that sense.
Interesting. Greg, you've got a question?
Yeah, thank you for the talk. This is fascinating. I love this topic of sort of edge computing versus server computing. And so my question would be that really the question at the center of the slide there, where should we place data in computation? So in answering that question, I'd be curious whether you've found what is the nature of the answer to that question? Is it a graph algorithm? Is it amenable to graph algorithms? Are those algorithms performed on the edge or on the server? Or are they simple query questions? What would the response look like, and sort of what's the nature of the computation involved in answering that question of what data needs to be where and how much data to move?
Yes. So, for instance, for me, the most natural way to understand this is just to think about the knowledge base. So, from a knowledge base, you can extract a lot of information, right? So, doing PageRank about characteristics that you are storing in the knowledge base may be important. So, for the tourist example, the Discover example, it was clear that you were just storing points of interest and tags, and you run the PageRank algorithm within the mobile device to understand what was the weight of each of the tags, right? But in other situations, you may have other types of objectives for your PageRank algorithm. When I was telling you about the micro routing, we have optimization, route optimization algorithms that go along with the graph database. So in that sense, you can run those optimization algorithms within the mobile device as well. So I'm talking about computations. I'm talking about real computations. You may be storing part of your data, which is live, within the mobile device and having algorithms that whenever they are needed. So for instance, imagine a guy who is interacting with Discover. This person may not be doing any like or comment. So you don't need to recompute the PageRank algorithm in order to have the tags sorted out by relevance. But whenever the guy has an interaction, it might not be even significant. So you may wait until the guy has, say, 5 interactions with the application, and in that case you recompute the PageRank. This is a decision that you take, but in terms of the amount of work that you are going to do, the amount of effort that you are going to do in the mobile device, this is not relevant, because for small graphs, relatively small, but 1,000 nodes in a graph for a knowledge base of a person who is interacting with a database of points of interest is not. I mean, it's a lot. 1,000 interactions is a lot, because people may have 2 or 3 interactions a day, so it needs a long story to keep all this information, right? So I'm not sure that I'm answering your question, but if you have any insight into what I said, go ahead,
Well,
and we can discuss
maybe
about that.
could follow up with an example and see what your thoughts in terms of how you would approach it. So you've got a traveling salesman, for instance, that lives in Boston, and he's going to LA, but he's got a layover in Chicago. So he's got Discover app, for instance. So what would be on his device in Boston, and then what would be on his device when he landed in Chicago, but was just passing through. So really didn't want to know anything about Chicago, but he's now located there. So would his graph get a new sort of network connection and download how much information about Chicago, right? And how would you know? How would you know to ask that question?
Yes.
The right answer. And then he's there for 2 hours, and he's off to LA. Do you keep that Chicago data, or do you drop it? And what does it mean to drop that on the edge device versus and then pick it up again in LA? And say he wants to know everything about LA. So then how do you?
Yes.
Yeah.
We are not going to avoid having data sent to the mobile device. But at least what we are going to do is to allow the device to ask for the data that the guy would like most to see, right? In the tourist case example, what we keep is the information about the tags and the relevance of the tag. So whenever we ask the server to send us new information, this server is going to send us information that is relevant for the person, right? So we are not going to save a lot of communication, but we are going to distribute this, the computation about the relevance of the tags for the user, for the specific user.
I see. So it'll be more like he like Cinnabon or hot dogs, and his device will remember that. And when he shows up in a new place, it'll know to sort of ask where the closest Cinnabon is.
Yeah.
Thank you.
Thanks, Greg.
Thank you.
Peter, you had some questions as well?
Yeah, hi. I've done things on ARM devices using RDFox, And also, I gather that Oxygraph can do the same. And I just wondered what's the best way about, and what sort of comparisons do you think one should be doing, taking a look at Sparxy versus these others, which are capable of providing all the advantages of edge computing that you're listing in the slide here, please.
In my understanding, the characteristics of, so for instance, with an RDF store, you cannot do routing, right? Well, I think that it would be more difficult than doing that in Sparxy. So some types of computations, of course, are going to be much easier in a graph database. One other thing that we learned from LDVC, the LDVC project, because in that project we had some partners which were RDF stores. The fact that RDF stores are basically relational stores with a layer on top that creates an RDF, I would say, illusion, and a pure graph database is that you are using relational and you have to compile for relational, right? While in the graph database, what you do is, of course, you are going to do joins, but you are not explicitly going to do joins, right? So for me, these are the most relevant characteristics. And also, I think that for the case of Sparxy, the fact that we use this type of very compressed storage is a significant value for us in an edge device as compared to an RDF store.
You know, that's interesting. That's the second time in the last couple of weeks I've heard someone make that characteristic that an RDF triple store is sitting on top of a relational database. And I think I only know of one instance where that's true, but does anybody else? I mean, I think Timbler, what's it called? Trimbler or Timbler or whatever that one's called, follows
Timber.
that pattern. But as far as I know,
Timber.ai.
yeah, but as far as I know, nobody else does.
Well, Virtuoso is on a column store, but I thought that most of the other ones are built from scratch as triple stores.
Yep.
Well, there's relational AI that's a multi-model database as well, and
yeah, and also there have been ones that use bits as storage in the same way that Sparxy seems to, so it's not a totally new concept.
Yeah, and well, all of them, pretty much all of them use long integers. Nobody actually uses the strings, but I don't know if that's compressed as these bits, but it's pretty compressed.
Yeah.
Luke, you still on? You haven't had a question about the partitioning. How's the partitioning achieved?
Okay, so what we do, every time that a new node is created, we try to include it in one of these chunks, of these 32-bit chunks that I was telling you. Whenever a chunk is filled, we create a new chunk that allows for new nodes to be included. Those chunks go into database pages, and these database pages feed into into operating system pages. I understand that we are talking about the same, right? You are talking about this. You were asking about this partitioning.
Yeah, but Luke doesn't have a mic today, so I'm just relaying the question.
Okay, so in any case, the idea is that the distribution of bitmaps is very biased towards very many of the bitmaps are very small, less than 256 56 bits. And this means that we can fit many of the bitmaps in a single page, in a single operating system page, which means that whenever we are accessing them, if we reorder the bitmaps in such a way that we express this locality into page is needed for the computations very much, right? Even if we don't do that, we exploit locality very much because of this reason, right? I hope I'm answering the question.
Okay. Well, we'll be sure to take a more close look at this. And is there a demo available?
You can access Sparxy Technologies webpage.
Yeah. And we're
And
on
if
the
you
bottom
want
of the hour, so
Yeah.
I'm sure folks have to go. Any other issues today, Dave or James? Thanks to Larry for
Yeah.
this really interesting
Yep.
presentation. A lot of good
was
stuff
great.
that you guys have been doing.
Mhm.
So
Yeah,
kudos to you.
Thank you very much.
definitely.
I guess
I'll be looking
just
for new. Okay. Yes.
I was just gonna make a quick plug for the data-centric architecture forums coming up first week of June. So, get off to our website. It's a in-person only, so you have to make that kind of commitment, but it's pretty economical.
And I'll get these slides in that web link posted here shortly this afternoon.
Mhm. There's a link in the chat for the data-centric architecture forum now, in case people aren't aware.
Thank you. Thanks for the announcements. Thanks again, Larry, and we'll see y'all next time.
Great.
Yep.
Thank you very much. See you
Bye-bye.
next
Thanks,
time. Bye-bye.
Bye now.